let's start with the abstract. Find the gap sentence. It's clear.
Yes,
there is it. Yeah. However, so okay, PCA actually can be used for capturing the common pattern from the time series dataset, but the performance is not that good, right? Because for the PCA we have to first we have to calculate the covariance matrix. But covariance matrix is just in the covariance matrix there is no temporal pattern, right? So because we average out all the temporal structure, so actually to capture the temporal structure using the PCA algorithm, many people try to use different correlation metrics, covariance metrics, such as time lag cross correlation metrics. But in this paper, they suggest the frequency dependent covariance metrics. So what is that? So time lag cross correlation is just we add some temporal variable, right? Time variable in here, right? And then if we average out with respect to t, then we will get this time lag cross correlation. But then what is the frequency dependent covariance matrix? This is just a Fourier transformation of c, tau, time lag covariance. So let's calculate this with using the very simple example here. So let's assume we have two variables. So these variables are oscillate along with the time, and then we have a noise term in here. Right? So we can compose these two terms as the noise and signal. Right? So typical PCA method just calculating the covariance matrix, right, in the specific time. In the this zero indicate actually correspond to the tau, so there's no time lag. And then after applying the PCA on this covariance matrix, you get this result. These green colored points are data points, and after applying the PCA on this C covariance matrix, then you will get this black arrow. Right? And actually, the red line corresponds to the signal direction, and blue circle corresponds to the noise direction. Okay, so this black arrow reflect the signal and noise direction, right? Both of them. So what if we use the FDPCA? So after calculating the time lag covariance, we have two terms. So first term is associated with the signal, the second term is associated with noise. And then this noise, covariance method, this noise is just have a very simple structure, right? So this rho actually corresponds to the covariance between this noise and this noise. Sorry, this noise and this noise. And so we also calculate the covariance related to the signal. So let's calculate the first term. S1 is the cosine omega 0 t plus epsilon, right here. And then after you add the time lag in S1, and you can get this equation. So let's simplify this using this formula, and then we can obtain this one. So why there is no time t? Because we average out with respect to time t, right? So, and we applied this calculation to the other element of the C, then we can get this time lag cross correlation matrix. So, and then we have to calculate FD correlation, right? By applying the Fourier transformation, then we can get this one, this formula. So, do you know how to calculate this one? So here delta function, here sigma delta is the delta function, right? If you apply the Fourier transformation to the delta function, then you will get the 1, right? And so if you apply the Fourier transformation to the cosine omega 0 tau, then you will get delta function as well, right? Because we can transform cosine function to the exponential function with the complex number, right? Then we can calculate. So, okay, then we can calculate the many covariance FD covariance matrix with respect to the omega, right? So we can change the omega now, the variable for the covariance matrix. Then let's calculate S0. Then second term will be 0, right? Because we have delta function in here. So we have this covariance matrix, and we know that this covariance matrix is related to the noise. Right? So if you apply the PCA, then you will get these PC vectors exactly corresponding to the noise direction. Right? And you can also calculate the IM vectors. In this case, so in this case, omega is not 0. Omega is omega 0. Then we can calculate the IM vectors. Then these IM vectors actually, the element of this IM vector is actually complex, right? But if we set the mu as 0, then we will have a real value. Mu, what is mu? Mu is just phase shifting here, right? Phase delay. So if we set the mu to the 0, then the direction is exactly corresponding to the signal. Right? Okay. So now we can get many covariance matrices bearing the omega. So what if mu is not 0? Then we can change this complex eigenvector to the real eigenvector. So then, you actually using the fixing gauge method, then you can transform this eigenvector to this eigenvector, and then if you change the time, you can get this trajectory. And this trajectory is exactly corresponding to the signal. Do you have any question?
So, yep.
Eigenvectors are not complex conjecture. I think usually eigenvectors are two eigenvectors are complex conjectures.
Oh, yeah.
But why is it these are not?
Two eigenvectors are complex. Why?
Uh,
You mean eigenvalues are complex?
Yeah, eigenvalues are complex. Yeah. I think eigenvectors are for the same eigenvalues and the two eigenvectors complex conjectures usually.
Yeah. So that means, okay. Complex conjecture.
So he is asking why two eigenvectors are not complex conjugate.
These two?
Conjugate.
Yeah.
Conjugate.
These two?
Yeah.
Yeah.
I think because the matrix is not real.
Yeah. Yeah, right.
If it is real, then
Yeah, this matrix is not permission matrix.
So I see. So eigenvalues also not complex conjugate, and eigenvectors are not complex conjugate because of the matrix is not.
It should be complex.
but eigenvalues maybe are complex conjugate because if you compute with that matrix, if you compute the characteristic polynomial, then the coefficients may be real, I think. If you add the trace is real, add the determinant, then maybe. I don't know, I'm not sure.
Okay, after this, we have to look into this. What is new here? New is the phase shift. We have two variables. We start with two variables. Actually, that is corresponding to this delta. Okay. Yeah. Okay. So I think to avoid the confusion about this delta function, change it. Okay. Then, anyway, we can, by applying the different omega frequency, we can get the different PC direction corresponding to the signal and corresponding to noise differently. Okay, let's apply this approach to the collective dynamic system. So, X actually indicate the electrical activity for individual neuron, and it have a decay coming here, and f function is just a linear function. They just considered f as the fx is equal to x, so you don't care about this. And then g is the connection weight, connection strength, and w is the synaptic weight. G is the connection coefficient. And this eta is corresponding to noise. Then we can change this equation to the matrix formation. So now A is minus identity matrix minus GW. So let's assume this random network. So they are connected randomly. So then the eigenvalue distribution of W is should have some circle distribution according to the random matrix theory.
So you mean they are on the circle?
On the circle, so real and
you mean inside or on the boundary? Maybe inside.
inside, yeah. Yeah, right, inside. So this color actually means the density. So after applying the Fourier transformation to this equation, then you will get this one, right?
Yeah.
So do you have any question about this?
Can you explain what is this network that you're showing? Like, is
Randomly connected. So if you set the number of connection, then you can randomly connect the node, right?
so the nodes have no particular meaning. It's not like one node is equal to one neuron in the brain or anything.
They consider auto connection, and they actually they use the random the normal distribution to get this W matrix. W matrix is the adjacent matrix. So yeah.
Okay.
And then after rearrange this equation with respect to the x, then we will get one, right? So then now it's time to calculate the FD covariance matrix. So yeah, the definition of the FD covariance matrix is this, and we can plug in the x, plug in this equation to the x position, then we will get this one. And this eta correlation actually corresponded to the delta function because they have no relation each other. So then we will get this one. Okay. Then, so in this network, you will get this time series. And if you calculate the power spectrum, then you will get this profile. How to calculate this power spectrum? The y-axis actually indicate the average of the diagonal elements in S. So in matrix X, you can collect the diagonal elements according to the omega. You can average, right? You will get this profile. And in the large omega, this profile follow the 1 over omega squared line, because in this equation, the magnitude of this is proportional to the 1 over omega squared, right? So, and okay, and actually they provide the probability. They provide the eigenvalue density function in the supplementary material, but that is too complex. But anyway, this matrix comes from the random matrix, right? So we know the random matrix property. They have maximum value, right? So using the random matrix property, we can calculate the maximum eigenvalue, which is x plus for the matrix X. So this is a formula of the maximum eigenvalue for matrix X. So if you so G if G is approached to the 1, then this maximum will go to the infinite. So we call it as the critical dynamics. So if you increase the G, if you approach the G to the 1, then this dynamic lose the fixed point. So that this system have a high instability. So anyway, and let's focus on this red profile here first. Then this red profile is corresponding to the omega 0 to 0. So we calculate this maximum IM value from the S0, right? So, and actually this omega 0 is actually corresponding to this value, this peak value. So we can calculate the G according to the. So what was the equation? I omega x omega after the Fourier transformation, right? Equal to minus x omega plus G W x omega and time omega, right? So then if you move this to this 1 plus I omega is delta equal to G W x omega plus 1. Then if we divide this term in the both side, in the both side, then we will get this coefficient, right? So magnitude of this coefficient is, so this is the effective coupling coefficient. So that means if you increase the omega, this coefficient will drop. So their connection is more weaker. Yeah, so then if you apply the omega equals 0, if you apply the omega equals 0, you will get this G close to the 1, right? Then if G approaches to the 1, you will get critical dynamics, right? Okay, and the largest IM value will be increased infinity. So let's consider the different system. So everything is same, but we will change the network. Okay. So before we proceed, what is the IM value of A? Right. So so we have two matrices, right? Here, if these two matrices satisfy this condition, commutable, then the IM value of these matrices is, right? So, okay. Then this IM value of A have a relationship with the IM value of W. Then, okay, let's consider this system. So W have this structure. So J is symmetry random matrix. So you have two populations here. So A population connected each other with random connection. Right? B population also have same structure, but they affect to the other population differently. So A population suppress the other population, and B population activate the other population, right? According to this matrix. Then how can we find the relationship between eigenvalue lambda omega, lambda w, and lambda j? How can you obtain? So we can express this matrix as the this matrix multiplication of this matrix. Actually, this is the Kronecker product, right? Law product. I think you introduced this.
You mean tensor product?
Tensor product, yeah. Right.
Yes, yes.
Yeah, tensor,
Product. Okay.
right? If these two matrices, so what is the eigenvalue of this matrix? Eigenvalue of this W matrix is multiplication of eigenvalue of M and eigenvalue of J. If they have, yeah. So if you calculate the eigenvalue for values from the M, then you will get this eigenvalue. And so I already told you that J is the random matrix, right? Random symmetry. So we can use the random matrix theory, right? So they assume the specific random matrix, and that eigenvalue of that random matrix have a maximum of 2. So after multiply, you will get this eigenvalue of W, and the maximum of eigenvalue for J is 2. Then maximum eigenvalue of the W is this. Right? Lambda J is. So if the system stays stable, then real part of this eigenvalue should be lower than 0, isn't it? So, yeah, if the system stays stable, then this condition should be satisfied. Then we know the this matrix, this eigenvalue, but we don't know about the G. But if we plug this expression to this, then we can get this critical coefficient G. Right. So do you have any question? So let's plug in these two values to the this equation to get lambda A. Then finally we can get this complex number, imaginary number, and from this we can get the frequency. Okay, so this frequency is the collective frequency. So yeah, we have this collective frequency, and if we draw the time series of this system, then we can get the oscillation with period of pi over beta g, which is exactly corresponding to the critical collective frequency. Right? So now it's time to calculate S at the covariance. And after that, we will get this profile. And as you can see here, omega C at the omega c, this S have sharp peak. So, okay, then let's compute the eigenvalue distribution. Okay, let's focus on this green profile. At the critical collective frequency, the largest eigenvalue of the S is much larger than others. Right? So that means if we obtain the eigenvalue profile from the FD covariance, then we can infer the dynamics according to the omega. Actually, that is the key point of this work. So they applied this approach to the EEG profile. And then they calculate S numerically. From this S, they obtain the G profile using the specific model. Okay. Then in this profile, I think the alpha frequency is corresponding to about the 10 hertz, right? 10 hertz frequency, isn't it? So in this range, frequency range, they get some peak here. So if you draw the histogram for the eigenvalue of S at this range, then you will get this profile. So in this profile, actually green line means corresponding to the eigenvalue profile of the random matrix, and black line indicate the power law. I mean, in the previous profile, they near the critical dynamics, they follow the power law, right? Here, so they show that in this at this alpha frequency, the eigenvalue distribution follow the power eigenvalue of the S. And then using the using the eigenvector corresponding to the largest eigenvalue at this frequency, they obtain this special pattern. Right? So they argued that this pattern exactly corresponding to the dynamics at near the 10 Hz. Okay, so they also applied this approach to the patient with the Parkinson symptom. So in this profile, they argued that there is a small hump in here, and I don't know, compared to this profile, I cannot find any difference, but they mentioned that the critical dynamics is present in both cases. Yeah. But I don't know why they compare these two result. Anyway, but still the profile of G, if you see the profile of G, there is more prominent peak near the alpha frequency. Okay. So, yeah. Today's message is that we can use FDTCA to get temporal pattern from the time series data, especially oscillatory time series data. And using the eigenvalue profile distribution, we can infer that dynamics is corresponding to the critical dynamics or not. So, yeah, that is today's, yeah. So thank you for listening. Do you have any question?
Can you go to the last slide?
Okay. This
before. So the picture in B2 is from the region of red region. I think you said.
Red region
I mean near the criticality.
near
The critical region.
Yeah, I think so.
B2 is.
Yeah. And then you can get the IN value and IN vector at the T.
T. Well,
Uh, leading IN.
I thought B2 or C2 are just time series data. No.
Okay, then I might mislead.
No. I mean,
Yeah, this one is time series data, but anyway, we can get some pattern from the IM vector. So I don't know this B3 is corresponding to that pattern, but there's time, right? So now I'm confused.
yeah. I mean, they argue that Parkinson's disease, people have more synchrony in the brain, as you can see. So all of them are red or all of them are blue, but
Yeah, but they have some shifting here, is it?
shifting. I mean, at time T1, most of them are blue.
Except the edges?
Yeah.
Okay.
And T2, most of them are red. In contrast, normal people, they are mixed.
Especially the
Yeah, but
Yeah.
I don't know why. Okay.
Well, I'm confusing
Mm.
things now. So previously, with the example, we just calculated the Fourier transform of the
Yeah.
series and
Yes, right.
how this changes according to some network.
Mhm.
But the title of this research is something FDPCA.
Mhm.
What is the resulting value of PCA?
IM value distribution.
I give them this.
Yeah, from this distribution, if the IM value distribution follow the power law, here they argue that this dynamics, this system show the critical dynamics at this omega 1 corresponding to this profile.
Uh,
Mm. Okay, no more question? Let's wrap up.